logarithmic functions. So we're going to learn about writing equivalent forms for exponential and logarithmic functions, and write, evaluate, and graph logarithmic functions today. So you just did that lesson where you learned a little bit about logarithms, and we're going to get into it, the beginning parts of it today. So it says, how many times would you have to double $1 before you had $8? You could use an exponential equation to model this situation. So for instance, you could do 1 times 2 to the x equals 8. You may be able to solve this equation by using mental math if you know that 2 cubed is equal to 8. So you would have to double the dollar 3 times to have $8. Well, the thing is that lots of times that's not so simple. What about doubling the dollar to get $512? You could solve that equation also, that 2 to the x, just like we did 2 to the x equals 8, by using inverse operations. So when we talk about the last couple lessons, you've looked at inverse operations with linear functions. We're going to look at inverse operations with exponential functions today. And when we look at the inverse of an exponential, we're actually talking about logarithms, something called logarithms. And if you look at your calculator, you'll see that above your, or you have keys over here on your left side where there is the word log written there. And above that's 10 to the power of x. And we'll talk about how they're related more today and tomorrow in the lesson, and what you were actually doing with the logarithms. But it works with exponents. So we can write an exponential equation as a logarithmic equation and vice versa. So here is, right, so this is going to be your friend for a little while. This general form for taking an exponential equation and writing it as a logarithmic equation. And this is how so we would say b to the power of x equals a. When we read the logarithmic part, we say the log base b of a is equal to x. Did you guys get note cards last week? Okay, all right, Mrs. Moskowitz gave them to you? Okay, good. All right, so notice where things go. We have the base b, and that comes over here, and that's the base for the logarithm. The exponent is what the logarithm equals. And then our answer here, a, is what we're taking the log of. Okay. So it's the log base b of my answer from the exponential equation is equal to the exponent. And so really all a logarithm is an exponent. We're finding an exponent. Okay. So the first thing we're going to do is we're just going to practice writing from exponential equation to logarithmic, and from logarithmic back to exponential. So you get used to doing that. All right, so we want to write each exponential equation in logarithmic form. So make sure you do realize that the base, when we write the logarithm, the base is a subscript. Everybody knows what a subscript is, right? Okay, it's down below. Okay, it's not in the same line, it's down below. So for this one here, I would say the log. The base for this exponential equation is 3. The answer is 243, so that goes here. And that equals the exponent of 5. So for the next one, we have the log. The base is 25, so that's a subscript down here of 5 is equal to the exponent of 1/2. Oh, and this one we just did on the exercise we did. This would be the log base 10 of 10,000 equals 4. Okay, and you guys go ahead and write the other two. Okay, so now, oops, I forgot, I've got to go down here. Okay, now we're going to go the other direction. Okay, we're going to convert them from logarithmic form to exponential form. Now, so the thing is when we look at this form here, then all we're doing is going backwards. Okay? The base is my base still. The answer is my exponent. And whatever this value of a is here, then that's going to be the value of a there. Okay? Those go switch back and forth both ways. So this, I have a base 9, so I'm going to say 9 raised to the first power is equal to 9. And the one thing to remember is that these always have to be true statements. Okay? They are true equations. And if you ever get one that's false when you look at exponentially, then you've made a mistake. Okay? So 2 to the 9th power equals 512. And 8 to the 1/3 power equals 2. So we're taking the base raised to the exponent, what it's equal to, and then that equals our number here. Okay, so a logarithm is an exponent, so the rules of exponents apply to logarithms. You may have noticed the following properties in the last example. So we have special properties for logarithms here. If I have logarithm base b, so if I have log base b of b equals 1. So that means that b to the first power is b. Okay? That's true, isn't it? Anything to the power of 1 is itself. And so here, their example, the log base 10 of 10 is equal to 1 because 10 to the first power is 10. So you can always note then that if these two things are the same, okay, it's always going to be equal to 1. It's always going to be equal to 1. Okay? So if the base and the of part, okay, if those are always the same, it's going to be equal to 1. So if I had log base 29 of 29, that would be equal to 1. And that should make sense because this is in logarithmic form, right? Okay, it's logarithmic form. If I change it to exponential form, it would be 29 to the first power equals 29. Is that a true statement? Yeah. Sure it is. 29 raised to the first power is 29. Okay. So the logarithm of base b, and we have the logarithm of 1. Okay, well, anything to the power of 0 is 1. So if we have the log base b of any number, okay, or of 1, I should say, it's always going to be equal to 0. The log base b of 1 is equal to 0. So if this number here is 1, it's got to be 0. because b to any power, or b to the power of 0 is equal to 1. Okay. So a logarithm of base 10 is called a common logarithm. If no base is written for a logarithm, the base is assumed to be 10. For example, the log base 5 means the log base 10 of 5. And that's that on your calculator, you have the log base 10. So if I put in here 100, what would we get? So this says if it's a log base of log of 100, that means it's a log base 10 of 100. So 10 to what power is 100? 10 to the second power, right? 10 squared is 100. See, this is an exponent, so it would be equal to 2 because 10 squared is 100. But if you're using the common logarithm base 10, your calculator does that for you. Actually, your calculator will do all of them for you, but I'll show you that a little bit later. If it was what? Yes. Okay. So it says evaluate logarithms by using mental math. Oh man, mental math. So the way I'm going to do these problems then, when they ask me to use mental math to solve these logarithms, I'm going to change them so that it looks like an exponential, because exponentials make more sense to me. Okay? So first of all, I don't like decimals. I prefer fractions. What's 0.01 as a fraction? 1 over what? 100, right? Okay. Tenths, 100. So this is the same as the log of 1 over 100. Now, when we have fractions, right, take this back over here. So when we were doing our warm-up, we had this stuff here. All right. If we get a fraction, that means the exponent is going to be negative. So we look at the denominator and say, okay, what's my base raised to what power gives me the denominator? Okay. So for instance, this denominator here is 16. So I would say, okay, 4 squared is 16. So since it's 1 over 16, I would say it's negative 2. 4 to the negative second is 1 over 16. Okay. So 10, because our base here, there's no base written here, so it's base 10. 10 to what power is 100? Okay, 10 squared is 100. So then if it's 1 over 100, then it would be 10 to the negative second. Yep. So this is equal to negative 2. Okay. Nope, it's just the answer is negative 2. The answer is the exponent. Okay. Right. So letter B. Okay. Think of it this way. 5 raised to what power is equal to 125? Okay. We wrote those down the other day, right? A couple weeks ago, we wrote down the cubes, and this is 3. The log base 5 of 125 is equal to 3 because 5 cubed is 125. So the letter C then, I'm thinking, okay, 5 to what power is 1/5? 5 to what power is 5? 1. But if it's 1/5, then it's going to be negative 1. Okay. Do letter B here. Okay. first thing I would do is change it to a fraction. Okay? Change that decimal to a fraction and see if that helps you. Because logarithms are inverses of exponential exponents, the inverse of an exponential function is a logarithmic function. So where we have y equals 2 to the x would be our function, the inverse of that would be the y equals the log base 2 of x. Those are inverses of each other. You may notice that the domain and range of each function are switched. So that's the thing we should notice last week when we were talking about inverses, is that the domain and range of them switch. So the domain for y equals 2 to the x power, here, the domain for this is all real numbers. I can put in any number I want for x and get an answer. The range for these numbers, the y values then, are all greater than 0. It's never going to touch 0. Okay? Never going to hit 0, never going to go below the x-axis when I'm talking about an exponential function. So the domain and range then for the logarithm switch. The domain for y equals log base 2 of x then is just the positive numbers, okay, greater than 0. And the range then is all real numbers, because it just keeps rising and falling forever. Because if I kept going, this red line would just keep going up and up and up and up and up forever. Okay? So these things you need to understand in all situations. Okay? If we're talking about exponential function, the domain is all real numbers. The range is y is greater than 0. If we're talking about exponential or logarithms, logarithm, the domain, x is greater than 0. The range is all real numbers. It always is, okay, for both of them. All right, so we're going to look at the graph. Okay. Here they want us to use x values of negative 2, 1, 0, negative 2, negative 1, 0, 1, and 2. They want us to graph this function and its inverse and describe the domain and range of the inverse function. So we have f of x equals 1.25 raised to the power of x, and I've already made the table here. So if we graph this function, so we got the 0.01, negative 1, and 0.8. Negative 2 and 0.64. 1 and 1.25. And 2 and 1.56. Which is this graph here. Okay. Now that's my function. Okay. Y equals, or f of x equals 1.25 raised to the power of x. So my inverse then is going to be, what do we do to graph the inverse function then? Okay, we're going to switch x and y, right? Okay, so that means then We'll use red for that, I guess. That means we're going to graph the point. I'm going to start with 1, 0. I like to start there. 1, 0. And I have 0.8 and negative 1. So it's about here. And then 0.64 and negative 2. 1.25 and 1. And 1.56 and 2. And then the graph of that. Like this. Okay. Now, what is the inverse? F inverse of x will equal what then? Okay. Well, all we're doing is switching from exponential to logarithm. Okay. What's the base here? 1.25. So that means this is the log with a base of 1.25 of x. They ask us for domain and range for all logarithmic functions. The domain and range is the same. The domain is x is greater than 0. The range is all real numbers. Oops, that's not very good. All real numbers. For all exponential functions, or all logarithmic functions, the domain is x is greater than 0. The range is all real numbers. Okay. Let's look at another one. F of x equals 1/2 to the power of x. Now, when I make these tables, I like to make these tables so when I start, I'll start in the middle at 0. Okay. So what's 1/2 raised to the power of 0? What's anything raised to the power of 0? 1. Okay, so 1 goes there. Okay. Okay. What's 1/2 to the power of 1? 1/2. Oh, come on, like that. Point. I'm going to use decimals. Okay. All right. So what's 1/2 squared then? 1/4. It's 1/2 times 1/2, right? That's 1/4. So for mine, I'm going to put 0.25 in. All right. So then I like to work backwards. Okay. All right. What's the opposite of multiplying by 1/2? Okay. Dividing by 1/2, which is the same as what? Multiplying by 2. So instead of when I'm going down, I'm multiplying by 1/2. So if I go up, then I'm going to multiply by 2. Okay. Well, so to get negative 1, what's 1/2? Or what's 1 times 2? 2, right? Okay. Because that would be 1/2 to the negative first power, which means I would take the reciprocal, which would make it 2. Okay. And then when I square 2, I get 4. Okay. So I've got the points, let's see, 0, 1, negative 1, 2, negative 2, 4. All right, so I got those 5 points there. All right. So then to do the inverse, we switch them. So we'd have 4, negative 2. 2, negative 1. 0, 0, 1. No, I mean 1, 0, excuse me. 0.51, 0.252. So we have this graph here. And so then our inverse function in this case is going to be the log. And since the base here for the exponent is 1/2, this base here is 1/2 of x. And once again, the domain x has to be greater than 0. Okay, we can see where this graph goes. We have an asymptote there. Everybody knows what an asymptote is, right? Means the line gets closer and closer to it, or the graph gets closer and closer to it, but never actually touches it. Yep. Okay, and then the range is all real numbers. And that's always the case for exponential functions. Domain, x is greater than 0. Range, all real numbers. Any questions? So what we did today, you got graphing of exponential functions and their inverse logarithms. And then a little bit of work with some mental math with the special properties of logarithms. And then basically converting from exponential to logarithmic form and back again. So and you should know, by the time you're done, you should be able to know this by heart. Okay, really easy to be able to switch from exponential to logarithmic because we'll be doing that a lot in the next few days.